Okay, can you see a slide that says explore science with a big I? Yes.
Yeah.
Okay, so let me go to one of my ones with sound. So let's try this.
Matter at the heart of a neutron star,
The slide that says explore science with a big I.
is on the brink of becoming a
Okay,
black
let me
hole.
go to one of my ones with sound.
Matter at the heart of a neutron star,
Explore science with a big I'm getting audio back from me about maybe a 15-second delay.
So we're getting some feedback from the YouTube. Sorry about that.
Yeah, okay. So see if you can hear this video.
decades, scientists have wondered about the properties of that matter, the densest in the universe we can measure, and what form it takes. Now they have new insights.
That's a little too low.
I turned it down when you were.
Oh, okay.
Yeah. Want me to turn it up?
Yeah, so we could hear that.
Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered.
Does that work?
Perfect.
Now, can you still see me while I'm giving the slides?
Yeah, you're off to the side.
Okay, all right. So I think we're good. Well, while you're doing your business meeting, I'm just going to throw in a couple of slides that I was adding before to my other presentation. But I'm fine. I'm ready to go whenever you guys are.
Yeah, now we're having a hard time hearing you.
Oh, okay.
Oh, okay. Okay. No, I think we're okay. Just turn the volume down.
If there is in German, I can't log in, but you log in here.
Yeah. Be live on YouTube right now. I don't know why it's not showing up. Oh, here live now. Sounds good remotely.
No, I had it here.
So Michelle, did you need a little bit of time to change some slides around?
It's no emergency. I mean, I can give this talk too. It's similar to what I was going to give. But if you guys are having a bit of a business meeting or something, or did you want me to start like right away? How do you want to do?
Would you rather have a little bit of time that we do the business meeting first?
Sure. Yeah, that's fine. Give me,
All right.
a little bit of time is fine, and then I'll
do that then.
sounds good.
All right. So we're just going to re-enable this. All right. So Michelle, you'll be in the background for a bit. All right. So we'll do the business meeting. It'll be maybe like 30 minutes or so. And then we'll come back.
Hello, everyone, and welcome to the monthly DVAA meeting. My name is Jan Rush. I'm president, and we have lots of activities coming up this month that we'd like to share with you. I always like to start with something that I saw in the last month that really kind of got me excited and was interesting. And this month, it was this information about Mons on Venus, and this is a artist conception.
I have to share. Sorry about that. A little confusion here. I don't want that. There is the clicker actually. I don't have it. Okay, so we'll just use here it is. Okay, now we're up.
Okay. So what got me so excited this month was this article that appeared in Sky and Telescope just in March. And these are data from 1991. So it's just exciting to me that people are still discovering things, looking at data from 1991. This is from the Magellan spacecraft. And it was a manual review of decades-old data. And what they found was evidence of active volcanism on Venus for the first time. So if you can see where the arrow is there, there's a very different appearance of that vent that changed shape during the time when it was being observed. And so that's evidence of active volcanism. Exciting stuff. All right, let's get to what's happening this month. Tomorrow and the next day, I know many of you are planning to go, is the Northeast Astronomy Forum and Space Expo. And this hasn't happened for since before the pandemic. So they are rip roaring. They have a lot of things going on. Take a look down there at the photo in the lower right. You'll see what the floor looks like. It's full of vendors. There are lots of talks. The planetarium will be showing shows all the time. There's a kids program and solar observing. So if any of you are up for a 2.5-hour drive up to Rockland, New York, it's a fun time. And we have some overnight star parties we wanted to bring to your attention. These were in the newsletter last month, but if you didn't catch them, here's a list. The South Jersey Astronomy Club is having a star party April 25th to 23rd. And some of these star parties is nice because you don't have to decide to go until you get to see what the weather will be like. And this is one of the ones where you can actually pay your $20 there. You don't have to register in advance. We're also having a DVAA member spring field trip. This is in a lodge, and the lodge is full. But if there's anyone who really wants to go, you can always come set up your equipment with us and on the field at the lodge, and either camp at the Cherry Springs Park or stay in a motel in Coudersport, which is 17 miles away. So if anyone would like to join us, those options are still available. Then there's the York County Star Party in June, another one where you can register after you figure out what the what weather's going to be. The official Cherry Springs Star Party was sold out at the end of March, and this is earlier than I have ever seen it before. 3 months ahead of time, it was sold out. But that's okay, because the nicest time to go to Cherry Springs is actually maybe when they're not having a big star party like this, because this star party is very, very crowded, lots of people. It's fun to experience once, but if you're one of those people who wants to go to Cherry Springs, try it out during new moon when there's not a big star party there. Any time at all during the week is good, or weekends that are not having this star party is good. So if anybody wants to hear more about how you actually, what the options are for going to Cherry Springs, talk to me after the meeting. I've been there a lot of times, and I've probably done every kind of permutation there is. And the last thing on the near term is the Greenbank Star Quest in Greenbank, West Virginia. This is an interesting star party because it has lodging. So you don't have to camp. You can just set up your equipment on the field and then go to the bunkhouse, and they have food and lodging taken care of. That's why it's a bit more expensive. And they do have an air-conditioned auditorium for talks as well, and a kids program. So that's really a nice star party that is worth the drive a couple of times in your life. And I did want to mention that if you're bound and determined to go to one of the big Cherry Springs star party, watch out for the registration for the Black Forest Star Party, which is also held at Cherry Springs Park, and that's in September. Registration was not open the last time I looked, but it is. It will be open pretty soon, probably. And of course, there's our own star parties, not overnight, but we had a great star party for our kickoff for this year in March. And the next one will be April 29th. The rain cloud date is April 30th. If you register for the event online, you will get last minute weather information. So give us your email or go to the website, register for the event, and you'll get updates either with text or email, whichever you'd like to provide. We're not having a telephone hotline this year. We're going to do everything through the website or email and texting. Also, one of our junior members is Daniel Adibi, is setting up an area especially for kids and teens. So if anyone is going to this website with someone who's a younger person, look for that special area. It's going to be a gathering place for all the younger members and visitors. And he'll be going through some things from a kid's perspective of, you know, how you get into telescope observing, what to look for, and that kind of stuff. Now, this year for the Valley Forge Star Party, we are, each Star Party needs a local captain. I mean, a captain of the Star Party. And the reason that is last year, one time we actually had an event when the public showed up, but there weren't any telescopes. And it was because the weather was really iffy. So we decided the best way to do that is to have one person, at least one or two people in charge of every Star Party. And basically what you're guaranteeing to do is that you'll show up and with your telescope and show the stars to whoever the public shows up. So we have this month covered, but we need some volunteers for the rest of the year. So please consider volunteering. I'd say if you've been to at least one Valley Forge Star Party in the past, then you know what it's all about. You can probably do this job because you don't have to be an expert to do it. It's just a matter of showing up with your telescope and showing people, you know, things that are up. That usually the moon is up, and that's a big one. So let me know if you'd like to volunteer for one of these dates. And finally, we set up a clinic to come, or that's coming up. Many people asked to be for a clinic on Schmidt-Cassegrain collimation, which is a little different than the collimation clinic we had previously, which was for reflectors. So if people are already signing up, it's pretty popular. So if you'd like to sign up, go to the webpage and register. It's going to be at Heidner Park, and the dates are May 6th and with a backup date of May 7th. Heidner Park is pretty close to here. It's in Worcester Township. So you don't have to go far. So it's waiting for waiting for students. And it's going to be staffed by Barry Johnson, Joe Lamb, and Gary Trapezzano. So thanks to them for volunteering for this. And I did want to mention, again, this forum, groups.io. This is how people communicate regarding what they're going to be doing in terms of observing. It's sort of a real-time kind of communication device. So what you'll see on there is messages like, hey, I'm going to Green Lane to do observing on Wednesday. Join me, something like that. Only 122 people are signed up for this, and we have 208 members. So there's a lot of people who haven't taken this step, and it is something that you are missing. You could be missing out on if you haven't signed up for it. You have to sign up separately from membership. So all you need to do is go to dva.groups.io, and it'll take you through the steps of what to do to sign up. Okay, so we have a couple of chair reports. Ryan, welcoming committee.
Hello, I'm Brian Lee, the welcoming chair. Kind of like this month, actually, we have two new members, Dylan Paré and James Pavlock. And then we have one returning member. I know quite a few people know this man, Robert Materi.
Yay.
Okay, thanks. So I don't see Bill here. He was going to come, but maybe something came up. So one thing I would like to mention that Bill was going to talk about, which is the Green Lane Park master plan. So Green Lane Park is a place that's pretty dark. It's about half an hour away from here, a little more maybe. But a lot of people like to go there for dark sky observing. And they decided they're going to they got money to make improvements in the park. And they're taking public comment on how the master plan will evolve. So you can imagine somebody might say, hey, we want the whole park to be lighted up bright. So it's really important that all of us jump in there, go to the website and comment and let them know how wonderful the park is for astronomy. There's a great article in last month's newsletter that Bill wrote about this. And I know many people went to the meeting, the public meeting that was held. There are going to be 4 public meetings total. But I really encourage you to get involved because this is really important for this club. It's one of the best spots we have for dark sky observing. And actually, we're going to hold the other items for Bill until he's here. Lou, do you have any announcements? Maybe you want to say anything about Green Lane if you know anything more. Okay.
Actually, as Jan was mentioning, Green Lane Park is developing their new master plan. They have the survey online for us to fill out. It's very important that every one of us participate and put in our 2 cents of what we want. If there is a place in the park that you like, particular for observing, and it's not currently someplace that we normally go, you should speak out and mention that. Where's the park? Green Lane Park, well, it's not in one place. It's a very long park. It's along the Green Lane River, which is dammed up on Route 29. One of the main observing places that we go to is practically on the corner of Route 29 and Knight Road. Specifically, it's the Red Trail parking area. Now, there is a parking area there, but also behind the parking area, there's a big grass field. Do not be afraid to drive your car onto there. It's a staging area for the equine clubs. The only thing I should be warn you is just be careful where you step. One of my ideas there was, I'm not sure how this would fly, but hoping that we can have a separate area of our own in that area. If they would just mow down just a little more further west on that lot. And that way, it might do a little bit to keep the traffic lights away. The other thing you can suggest is how we can keep the traffic lights under control in that area. But, you know, we can leave all the rest of this for Bill. What I do want to mention, though, is if you want to be part of the astrophotography group, we have monthly meetings and we hold them the Wednesday prior to this meeting. So it's 2 days before our general meeting. And the reason why we do that is to coincide with the moon. We don't want to take away moonless nights from observing. Does anybody have any questions? Is this 18054? I'm gonna guess that's what it is because I live across the street and that's my zip code. You know, and again, I live across the street, literally about 400 yards away as the crow flies. So if you've gone up there and forgotten something, an extension cord, well, I don't know if you have a generator or whatever, but you know, feel free to get a hold of me if I'm awake and if I'm home. You know, I'll be happy to help.
What if I forget to bring my steak dinner?
What if you forget to bring your steak? Well, I don't eat meat, so
More for me then.
yeah, there you go. But yeah, once in a while, I'd like to, you know, barbecue ahead of time. If there's only one or two people, you guys are more than welcome to use my backyard. I have electricity hooked up outside there. I have an observatory. You know, just send me a text or you can get a hold of me. My number is listed on the webpage there. If I tell you now, you're gonna forget. But at any rate, any more real questions? No? Okay. Back to Jim.
Thank you, Lou. Anyone else with announcements? Okay, I did want to mention the exciting news that we've brought back the DVAA raffle. This used to be a monthly feature of our meetings. Now we're going to do it quarterly, so we have a little more time to accumulate those really great goodies. So back there on the corner table, Ken Kopplinger has nicely volunteered to run the raffle. There are a lot of goodies back there, and the way it works is you, before the meeting starts, you go and buy as many tickets as you like. They're $1. And then after the meeting, we'll draw a ticket, and if your name gets called, you get to go and select whatever you want off the table. Okay, so it's a really good deal. And furthermore, if you have some stuff hanging around in your closet that you no longer need and it's astronomy related, just bring it into the meeting and give it to Ken, or if he's not there, give it to me, and we'll get it in the next raffle, the upcoming raffle. Okay. Any questions before we go to our featured presenter? Ken. Yeah.
Again, for the back, so we're down.
I just wanted to put a plug in. If any of you are going south this summer, come down to the NASA facility at Wallops Island. I work part-time there as a volunteer as a science tour guide. It's a really cool facility if you've never seen it. If you happen to be down at Chincoteague or Assateague. Assateague's a great place to do astronomy observing, by the way. Down there, much better than Green Lane, by the way.
Thank you. Yeah, you want to know any more about that? Let's talk to Ken after the meeting. Okay, I'm going to turn it over to Jeremy then to introduce our featured speaker.
All right, thanks, Jen. Let me do a little housekeeping around here. So Michelle, are you about ready?
Yes, I'm fine, whenever you are.
All right, so I'll just give a quick update on programs, and then we'll go right to Michelle's talk. So I'm Jeremy Carlo, the programs chair. So a little bit about some upcoming presentations. In May, we're going to have John Homka, who's a member of the Chesmont Club, and he's going to be talking about building his 24-inch f3 telescope, including night vision optics and a couple of other really cool things. In June, we're going to have Steve Connard. You may remember he came and talked to us about New Horizons at Pluto and Arrokoth. So he's going to tell us the latest about what he's doing. In July, we're going to have Ray Harris. He's a member of the Lehigh Valley Club, and he's going to be talking about development of star charts, which sounds really interesting. August, we're actually going to have a double meeting because we have a blue moon that month. So, you know, we try to keep our meetings aligned with the full moon. So it either meant we have to have 2 meetings in 1 month, or there's like a big 8-week gap. So we decided to go with 2 meetings. So on August 4th, we're going to have Harold Goldner, who I think all of us know. He'll be giving a presentation. He'll be talking about Shakespeare and literature and how that relates to astronomy. August 25, we're going to have an outdoor meeting at Fort Washington State Park, similar to what we did last year. Then in September, we're going to have John Conrad coming back, and he's going to talk about the OSIRIS-REx mission, which is actually supposed to be landing, I think, 2 days after the meeting. So that'll be very timely for that. That's what I've got scheduled so far. We are planning on having a trivia night, maybe sort of like a pub quizzo, something like that. We're thinking maybe December for that. So start studying up. All right, so tonight I'm very pleased to have a very great speaker. We're going to have Michelle Thaler. She's the Assistant Director for Science Communication at the NASA Goddard Space Flight Center. Michelle did her PhD at Georgia State University. She's been very active in both research and in education and public outreach. She gave a really great talk to us shortly after the Webb telescope launched. So that was really fun to have her for that. That was back when we were meeting on Zoom full time. Now we're back here, but Michelle is down in Maryland. So the Friday afternoon drive up Route 95 wasn't too, didn't seem too popular. So she's going to be joining us by Zoom. So this is a brand new thing that we're going to try out, and hopefully it works pretty well. So I think if we hold questions till the end, that would be the best, because she probably can't hear you out in the audience there. And for those on YouTube, also hold your questions till the end, and we will try to do everything then. All right, Michelle, take it away.
Well, thank you. It's really nice to be here. And to tell you the truth, it wasn't even the drive up 95 that was the problem. I'm actually in Milwaukee, Wisconsin. So I'm a little bit farther away than I normally am. Can you see me on the screen, or there I am. Hi. So I'm actually here in beautiful Milwaukee, Wisconsin. So I'm here visiting my parents for the weekend. And that's the nice thing about Zoom, is being able to be here with you tonight. I do have some updates from Webb I can share. I also want to talk about one of our smaller missions that sometimes doesn't get a lot of attention, but there are some results, some science results coming out of it that are just absolutely bending my mind. I mean, it is just really incredible science. And speaking of incredible science, I really want to reiterate that shout out that Wallops Island got, the Wallops launch facility. That's actually a lot more interesting than a lot of people give it credit for. And there's a lot of extremely important science that is centered there or goes on there. It's where we do a lot of our sounding rocket launches. There is so much incredible science that can be done on these relatively inexpensive suborbital launches. It's a great way to train our sort of next generation of science leaders. You know, when you want to actually put an instrument up on a satellite and build a very expensive $1 billion version of it, you need to make sure it's flown in space before. It's a place where you get space qualified. It also is a place where we actually run our super pressure balloon program. That's been in the news a lot recently. NASA was a little worried about our balloons getting shot down there for a while. But the balloons are not necessarily launched from Wallops, but Wallops is where the whole thing is managed. And then we launch a lot of balloons specifically from Antarctica and also up in the north parts of the latitudes as well. They do a lot of heliophysics experiments on the auroras, but also, I mean, the thing that's so useful about the Antarctica launches is that there's a very predictable current of air all the way along Antarctica. It just goes all the way around that big island. And if you can launch a balloon up into that big circular current, it can stay up there for months. And so it's almost like the equivalent of having, you know, sort of a short-term satellite. You can get fairly high and you can be up in the air for a long time. And we do things like cosmology experiments that have the microwave background readings, you're looking for the remnant radiation of the Big Bang, all of that. So it's a really interesting place to be. So we'll talk a bit about, you know, some of the big budget science and then also some of the amazing and innovative missions as well. So, okay, so to get things started, let me share my screen here. Okay. Share my presentation. Okay, good. Looks like you can see that. And let me just start on this slide over here. So we were talking, don't even try to read this, by the way. This is what we call a shock and awe chart. So these are all a bunch of acronyms. But the thing that's interesting about all of these acronyms is it shows you all of the active science missions that NASA's running. So more important than the names or the little acronyms is basically just the sheer number. At the moment, and it changes weekly when different missions are launched or different missions are decommissioned. We have about 110 active science missions. And it amazes me that a lot of people don't realize that NASA has this incredible portfolio of science missions. People hear about the Artemis program, the space station, but a lot of times they don't know all that we're doing. They're divided into the 4 science divisions that NASA is organized into, all the way up to NASA headquarters. You can see on the bottom left of the screen here all of the Earth science missions, and in front of the Earth is the moon, all the different moon missions that we have going on, science missions, that is. And then in the upper left here, you have all of our astrophysics missions looking beyond the solar system. And then this is all of our planetary and sun-centered missions over on this half of the chart. A lot of you probably know the sun is going up into its 11-year expected solar maximum in the next couple of years. About 3 weeks ago, we missed a bullet. The sun gave off a gigantic coronal mass ejection. For those of you that follow such things, this was equivalent to something called the Carrington event in the 1850s. In the 1850s, the lucky thing was the best we had for electronics were telegraph lines. And there was so much electrical current being forced through the Earth's magnetosphere by this big coronal mass ejection that the telegraphs ran without power. You could actually send telegraph signals without connecting it to a battery. And then later on in the day, the telegraph wires caught fire in some places. A coronal mass ejection equivalent to that went off about 3 weeks ago in early March. Luckily for us, it went off on the other side of the sun. But had that gone towards us, I think we would probably be in a global catastrophe right now. It's not biologically harmful. Our atmosphere absorbs all of the particles that are harmful to us, at least most of them. But it puts so much electrical current into our system, it would have brought down all of the Earth's electrical grids. So I think there'd be massive blackouts, trillions of dollars of damage. That's my mom in the background. You can all say hi. So, okay. So, in that portfolio of science, we have things like the web that are very, very expensive, $10 billion price tags. And then we have things that are only in the hundreds of millions of dollars. I know that says only, but that's a very small amount of money to do the science that you need. So I think I may have given you some of these slides before, and I apologize if I have, but there won't be a whole lot of repeat. But as we began to see the images come off the James Webb Space Telescope over the last year, this of course made the news. They were better than we expected. There was lower noise in the instruments. Things were incredibly clear. The focusing mechanisms worked even better than we'd hoped. As you know, there are 18 mirror segments that all independently focus, independently tip and tilt and move. They can move in and out as well. And they have both sort of rough guidance, where you can sort of move the whole mirror around. But then there's actually fine focusing mechanisms where there are tiny actuators that just push and pull on the mirrors a little bit. And basically distort the mirrors by a couple hundred atoms at a time, tiny, tiny little bits. And those worked incredibly well. And so, the idea of taking a picture of Jupiter like this, so clearly from near the Earth, the Webb, of course, 1 million miles away out past the moon, but still very much part of the Earth-Moon system, going around the solar system with the Earth and the sun, with the Earth and the moon. So this is a beautiful infrared picture of Jupiter, and some things, of course, show up better in infrared and heat light. Immediately, what jumped out at us is that you could see the very, very tenuous ring of Jupiter over here. This little, tiny little weak ring, basically, of Jupiter wouldn't even be visible to you if you were very close to Jupiter in visible light. It's very dark, very sparse dust, but that dust shows up a bit in the infrared. And then you can see the auroras, the north and south poles lighting up in the infrared. And the red spot looks incredibly wonderful here as a slightly warmer area, giving off a bit more infrared radiation. The cloud tops are still very cold to us. They're still on the order of, somewhere between 50 and 100 degrees above absolute zero. But even so, that area is warmer than the rest of the cloud tops and a couple of the minor moons. So wonderful picture there. What came out more recently in just the last few weeks that I'm sure a lot of you have seen is the picture of Uranus. And I had seen the picture of Neptune before. Hopefully you've seen that. And that was, again, far better than I ever thought we would get pictures of Neptune with the Webb. In the case of Uranus, there were things that even as somebody, I'm an astrophysicist, I'm not a planetary scientist, but I've taken, graduate level planetary science. And I'd never heard about these beautiful resonances in the rings. These very, very clear lanes of the ring dust. And another thing I had never heard about before is that there is a quote unquote polar cap on Uranus. Now, it's not anything like a solid ice polar cap. It's probably a bit misleading to use that, but there is something that happens in the atmosphere right when there's a change of seasons on Uranus. And, Uranus takes, a very long time to move all the way around, a little more than 80 years, all the way around the sun. And apparently, like I said, I didn't realize this, that when the seasons change, so the northern pole hemisphere is going to be coming out of spring now into summer. And when the seasons change for a little while, you get this sort of cloud formation right above the North Pole or the South Pole, but when the summer shifts over there. And this is not well understood. We don't really know what's going on in the atmosphere of Uranus. The thing that's kind of neat to me with this image as well, that when we flew by Uranus with Voyager 2, it really was featureless. It was a blue ball. And if you turn the contrast way up, you could see a little bit of ring structure going around the poles, which of course, in the case of Uranus, are facing us. The poles are facing onto us. Here you actually see some storm clouds similar to what we saw on Neptune when we flew by Neptune. Neptune had these really interesting storms. And our infrared image of Neptune shows that similar storms still exist there, but we had not seen them, at least I'd not seen them this clearly on Uranus before. So really, really amazing picture of Uranus from the Webb telescope. So the other thing, of course, that we're really ramping up and doing more and more is our study of exoplanet science. And the big goal, which we have done to some extent already, is to identify the chemistry of atmospheres. I mean, not just the mass of an exoplanet or how close it is to the sun or the temperature, but what can you say about the chemistry of the atmosphere? Is it similar to Earth? Is it very different? And I know that this is something that's going on right now. There are a lot of press releases toing and froing around NASA. So you mean when Webb was launched a year ago on Christmas, obviously there were early release observations, different things to check out. And we've been in our first year of real solid science. And with Webb, of course, there's always going to be a lag. People get the data back, they're writing the papers. So I would expect to see in the next 6 months to a year a flurry of spectacular results as all those papers are published. I mean, in some cases, all of the data for the early release observations was made public immediately. And some of the really amazing observations we haven't really been able to comment on yet because they haven't been published yet. And that now the papers are coming out, so I'll be able to do that. So just again, a little bit of a primer. The way we observe exoplanet atmospheres is right before or after the exoplanet eclipses or transits the star. The starlight will be shining through the atmosphere of the planet. And you see that here. So here's our little planet moving. And if I pause it, the planet is now beginning to block the light of the star. But you can see here in different layers of the atmosphere, the sunlight is now shining through different layers, getting closer and closer to the surface of the planet before the real eclipse begins. And so looking very carefully, you can actually even tease out different layers of the atmosphere at different wavelengths and see even something of the atmospheric structure, we hope. And the big thing that we're hoping this works for is, and you see here, one of the reasons Webb actually won approval to be developed starting in 1995 was that the infrared wavelengths that Webb looks at have some really important chemical signature lines. So if you pass that light through a spectrum, there are some very, very important lines, at least for looking for life-friendly environments, the detections of oxygen and water, methane, carbon dioxide, ozone. We certainly can't say anything like this for sure, but I've heard from a lot of people that study planetary atmospheres that if we can find water and carbon dioxide and oxygen and methane all present in an atmosphere, that's actually kind of hard to do without life. It's going to be beautifully frustrating because I mean that will not allow us to say 100% that there's life there, because maybe there's a planet that does this naturally that we don't understand how. But we hopefully sometime in the next, well, maybe even a few years, we'll be able to point at a star or look at a star through a telescope and say there's a planet that likely has life or very possibly has life around it. Like I said, that would be frustrating but wonderful. The big goal this year was to make great observations of the TRAPPIST planets. And that's going on right now. And they've already released some data for the innermost of the TRAPPIST planets, which are so warm that we do not expect them to be habitable. But then as you go a little bit farther away from the star, then these things are very solidly in what we call the habitable zone, which is an Earth-like environment, something that could have liquid water on its surface. So these are all being observed. I know that we've observed something called the secondary eclipse of these hot inner planets. The secondary eclipse means that, I mean, not only did we see the star light eclipsed when the planet moved across the star, but on the other side, the Webb telescope was actually picking up infrared light from the planet. And when the star blocked the planet, the light from the infrared light from the whole system went down as well. So that means we're going to be able to separate the light coming from the star and the light coming from the planet. Not only did the planet eclipse the star, but the star eclipsed the planet. And we actually saw the radiation drop, which means we had detected direct radiation from that planet. So you guys are all very well versed. So I'm sort of basing this at a very very interested level. If anybody doesn't know the TRAPPIST system, this system has at least 7 Earth-sized planets in unbelievably close orbits around a very dim red dwarf star. And this is a system that, if somebody had told me in science fiction this existed, I would never have believed it. I mean, you can see the scale. So they have sort of a blow up. Obviously, planets are not to scale with the orbits. There's no way you could do that in one chart. But you can see there at least the scale of the orbits, artist conceptions of the planets, and at least these 7 planets. There may be more, but these are the first 7 we've detected, could fit well within the orbit of Mercury. In fact, these 7 Earth-sized worlds are even not all that much larger than the Galilean moons of Jupiter. They're like twice that. So that's nuts. I mean, you would actually have, a sky full of planets hanging up there in the sky, be able to see, maybe even like details, if there's lava on a planet or if there are continents and oceans. I mean, it would be an amazing place to see. So that's one of the places that we're shooting for first. And I know that they're doing a lot of studies right now. The galaxy stuff, of course, that's coming out of Webb is also astounding and beautiful. Now, this is a large spiral galaxy that was observed by the Hubble Space Telescope. And I think that comparing the Hubble to Webb imagery, you really see where Webb has a very fundamental contribution to make. So on the left side is the Hubble image done in invisible light. And so you see a beautiful galaxy dominated by the starlight of hundreds of billions of stars. The center, the nucleus of the galaxy, is pretty much all just white, just kind of basically overexposed. You can't really see any detail. And then you do see the dark dust arms coming that trace the spiral arms. You can see those coming out of the nucleus. The dust is dark, it's absorbing light from the stars behind it. And then as we go to both near infrared Webb images, and in this image, I think both combines a bit of Hubble and Webb, you begin to start seeing the underlying dust now glow itself. You're not just looking at the starlight. The areas around the nucleus of the galaxy in the middle begin to really clear out. You can see farther and farther and deeper into the galaxy. And then the one that really gets me is a longer wavelength view of this galaxy from Webb, where now you're going into lower energy infrared, even lower energy. So you're picking up lower temperature things glowing. And here you really see the underlying skeletal structure of that galaxy. This is the dust that binds the galaxy together. All of this debris from dead stars over billions of years. The nucleus of the galaxy is now very clear to see. There appear to be lots of hugely bright star clusters orbiting what we very much assume is a supermassive black hole. And just the connective tissue of this galaxy, there are holes in the dust that were probably blown by supernovas or the formation of a huge cluster of stars that blew away that dust there. But a very different view of a galaxy, and one that you can really see what the contributions are of infrared. Yeah, just a close up on that. I just think it's beautiful. The nickname of this galaxy, and I forget what the Messier number, or the NGC number is. I forget what but this is called the Phantom Galaxy, and I know it just looks spooky and wonderful, almost like ripped fabric. The very cool dust that is connecting everything in the spiral arms. Now, as I mentioned, some of the things that were made public immediately because they were early release observations and the data was free to the public, it was just sort of to show everybody what sort of images we could take, were some of these looks at the deep sky, looking far out to where the galaxies now become just little smudges and dots. And this was one of my favorite stories. We actually were using one of the first images that we took of looking far out into the universe was not a very long exposure for a space telescope. It was 3 hours. And so, you know, you're all familiar with the Hubble deep fields. The Hubble looked at the same area for a month, you know, and that kind of thing. So this was sort of a checkout to see what we could see just with 3 hours, you know, basically go to lunch, turn the web on and come back and see what you got. I mean, it's a joke, but what happened is in 3 hours, in our first attempt, we imaged the farthest galaxy ever seen. And so, you know, we were now looking at galaxies that are easily within about 500 million years of the formation of the universe, the Big Bang. And they, of course, are yielding a lot of surprises. They don't make for the best images. They're all just these little smudges, but the smudges are incredibly profound. And of course, they're already challenging our ideas about what things were like, you know, back just a couple hundred millions of years after the Big Bang. And this was the one, by the way, that it didn't take a lot of scientific expertise. I mean, all you had to do is really read some of the photometrics, just how much light was coming in which wavelength, and you could tell what the redshift, how far away this galaxy was. And so people actually knew that we'd found the farthest galaxy before we published it. So that was, it was like, wait, let's get this published first. So, and we did. As we did deeper and deeper views of the universe, sort of seeing how far we could look out, looking at the galactic structure, you can see in these beautiful images the evidence of a lot of gravitational arcs, the distortion that's put there, probably by the presence of dark matter around galaxies, distorting the light. We're beginning to see things very, very far away. So these galaxies that you're looking at here, you know, we're looking back to a time again, just a couple 100 million years after the Big Bang. One of the things that I think is incredible, a little bit more recent, is that we are also able to see galaxies beginning to orbit around each other, forming sort of super clusters of galaxies. These are the seeds, the cores of what are going to become the galaxy super clusters. And again, this is very far away. In this case, we're looking back to a time about 1 billion years after the Big Bang. So not quite as far back as some of those other things, but we have a huge central galaxy that's actually being orbited by other large galaxy clusters. And so we're looking back to the time when some of this large scale structure began to form, when not just galaxies were forming, but clusters of galaxies all coming into these big gravitational wells together and beginning to orbit around each other. This is probably something that is the origin of a giant supermassive black hole. You know, there are already massive black holes in the centers of these galaxies, even 1 billion years after the Big Bang. And one of the ideas is, well, how do you form these super duper 10 billion solar mass black holes? It may be from some of these early giant galaxies converging into one. How you form black holes that soon, I think most of you know, is one of the big mysteries, because none of our computer models work. Even if you have two supermassive black holes orbiting around each other, it would seem to take the age of the universe before they'd actually be able to collide. But some people think if you have multiple black holes in galaxies, basically throwing stuff out, getting closer together, maybe that's how you can get these things to coalesce. And so that could be what we're looking at here, is the formation of something like that. And again, this is my last blob image, but I'll just sort of say that although these blobs that are only a couple pixels across, again, not spectacular images, these are, you may have heard about this, these are 6 galaxies, each of the center of these frames, where we're now looking back to a time, probably we're going on 400 million years after the Big Bang. I mean really the sort of dawn of galaxy formation, or so we thought. The thing is that these galaxies are all as massive as the Milky Way. They are very different from the Milky Way. They are very, very dense. So, I mean, I think that the analogy that I heard them use in one of the press articles was, if you think about a regular person, 5'9", 170 pounds, about this, these are baby galaxies that have the same mass. So they'd be 170 pounds, but they'd only be 3 inches tall. So what are these super dense, tiny early galaxies? This is not something we predicted. This is not something that we really knew existed out there. So we don't know how you get that much mass together so quickly. We don't know why they're so tight. Does it have something to do with supermassive black holes in the early universe? Maybe that's what everything is. I don't know. But these were surprises. We didn't expect such massive galaxies so far back in time, so soon after the Big Bang. And again, they're odd. They're not any type of galaxy that we've seen before. I know this looks a little bit technical, but the thing that really amazes me is we're now right up against a time called the reionization era. And this is what Webb had hoped to do. And I did not expect it to be happening so fast. I didn't think that we would have this like in the first 6 months of observation. But for those of you that have studied a little cosmology, I apologize. I know many of you know this and maybe some of you don't. There is a limit to how far you can easily see back into the universe, because actually the gas between the galaxies was in a different state for quite a while. For a while after the Big Bang, the gas between the galaxies was actually quite cold. It was neutral. And that meant in a cold hydrogen gas between the galaxies, you could form regular atoms. Electrons could get in orbits around nucleons, and you could mostly have hydrogen gas, hydrogen, a little bit of helium. And when you have cold gas with electrons, it's easy to absorb light. The electrons can absorb light, jump to different orbits. So cool, neutral hydrogen gas is actually quite opaque. It's difficult to see through. And so there's a limit somewhere roundabout, say, 200 to 300 years after the Big Bang. For a while, we're in this cosmic dark ages, and this may be where the first stars formed, and they're really going to be hard to see because the gas of the universe itself, the gas between the stars, was cold. And then what happened is all of that gas was extremely heated up to millions of degrees. Today, the gas between the galaxies, although it's very thin, so you don't need to worry about that, is millions of degrees hot. So it went from being cool and neutral to millions of degrees. And this was called the era of reionization, which is a fancy word for it. Everything heated up again. And we don't really know exactly why, but the big idea is that when these supermassive black holes first turned on and matter was falling into the black holes, and you had the first quasars, huge hot disks of material rotating around the black holes, that created so much heat, and there were jets and all of this stuff. It basically heated the entire universe up. The gas between the galaxies was heated to millions of degrees. So one of the reasons we've always been a little bit suspect as to whether we'll see one of the very first stars, one of the stars that's actually a first generation star, is that was probably all happening back in this cooler era. And but what we're hoping for is that this era where the gas is either cool or hot is kind of patchy. It didn't happen everywhere all at once. So if you're close to a big bright quasar and the quasar is heating everything up around it, maybe you can see farther in as opposed to an area where there isn't something heating it up. And some of these farthest galaxies that we're seeing are already, here you see the farthest galaxy Hubble has seen, we're already past that. So we're kind of into this region where we're getting into that cosmic dark ages. I think that's amazing. Okay, so that was my little review of the Webb. I wanted to change tacks a little bit and talk to you, as I said, about some kind of mind-blowing results that we're getting from a cheaper and smaller observatory. And unlike Webb, that looks at everything, it looks at planets like Jupiter, it looks at exoplanets, it looks at galaxies at the end of the universe. This is one of the advantages of building a very, very specific scientific instrument that only looks at one thing. There actually have been a couple other things we found. We found some interesting comets and stuff just kind of in the way. But I want to talk to you about a mission that is specifically designed to measure radiation coming from neutron stars. And again, most of you, I think, are familiar with neutron stars, but we'll go into what they are. They are some of the most amazing monsters in the universe. They're real. And we know of thousands of these things. And we study many of them. And a lot of people who get really excited by black holes, say, oh, the public loves black holes. All the people that I know that study neutron stars are like, neutron stars are even weirder. And the thing is, you can see them. They're not just a bottomless pit of gravity. They're there in front of you. And so I think that's really, these things are mind-blowing. So neutron stars are the collapsed core, the remnant of a massive star that has died and gone supernova. And we'll show you a little bit of a video about this. But what happens when a massive star dies is that the nuclear reactions finally die away in the core. There's no more heavy elements it can generate. And so all of a sudden the nuclear reactions shut down inside the core of a huge star. And the core collapses because the nuclear reactions are done and just the gravity of the core collapses. And then all of these layers of the star collapse on top of that poor core, collapse it even further. And as all of those layers of the star are rushing down, now there's no nuclear reaction to hold up the star. There are shock waves generated and everything collapsing on top of everything else. And that rips apart the star in a supernova explosion. But unlike most explosions where there's nothing left in the middle, everything just explodes, because the core was collapsed and everything was trying to collapse onto the core, you're often left with these little remnants, neutron stars, and they're called neutron stars because the gravity is so intense in the middle of that collapse that it actually crushes electrons into the nuclei of atoms, where they combine with protons to become neutrons. So they are literally mostly made of neutrons, and that's because the electrons were crushed into the nucleus by gravity. I mean, we're not used to gravity affecting what goes on inside a nucleus of an atom very much. So this is a really amazing thing. As you can see by this artist's conception, this is the size of a neutron star. They're about 20 miles across. And this is a neutron star size comparison to New York. We've got Manhattan here and Central Park. This would be a very bad day in Queens, as you can see. No, actually it'd be a very bad day for the Earth if a neutron star got anywhere near us, because the density is crazy. So you collapse about 2 times the mass of the sun into a 20-mile ball. And if you had a teaspoonful of neutron star material, that would have about as much mass as Mount Everest. So it would pass straight through the Earth like, an airplane going through air. I mean, it would barely notice that anything was there. So, this type of matter is, luckily for us, not something we can create in our labs. It is an exotic form of matter where the particles that we're familiar with, protons, neutrons, and even the quarks that make up protons and neutrons, there may be a different sort of particle physics going on here. So it's always fun for me when you can look, in the sky. In this case, neutron stars are so small, you're not going to be able to see them through a telescope, but you can certainly pick up their radiation. And, it's amazing to measure things that, right there in front of you is something that you don't have the physics to explain. It's like, okay, good, So again, just to recap, this is a Hubble Space Telescope picture of a dying star. Its nuclear reactions have largely shut off, and it's probably going through a bit of helium fusion at this point, and the star is forming what we call a beautiful planetary nebula. It's ripping apart, unraveling into space. And I know planetary nebulae are certainly one of my favorite things to observe. And then the thing that really kicks off the supernova explosion is that you've been fusing hydrogen into helium, then all of that in the core ran out. The gravity crushed the core down more, temperature goes up, and now finally you can fuse helium into other things too. And helium doesn't fuse as well as hydrogen. Simply, seriously, think about the electric repulsion. For hydrogen, you've got 1 proton and maybe a neutron, and the electrical charge of the proton keeps them apart unless you slam them together. And for helium, you now have 2, helium nuclei. That's like 4 times the amount of electric repulsion. They really don't want to get close to each other. But if you're really crushing the star's core in, then you begin to fuse helium. And then that cycle goes on until you hit iron. And iron is the end of it, because iron, if you fuse iron, it actually absorbs energy. You do not get energy out of iron fusion. And so all of a sudden, this core that's had an energy source, for millions of years, there's no energy coming out, and it collapses violently. And so, iron is the element. When you try to fuse iron inside the core of a star, that's when all hell breaks loose, because everything just collapses. And there's the Crab Nebula, which is one of the more famous supernova remnants in the sky. The Crab Nebula is still moving outward at 2 million miles an hour. It's now many light years across, but there you see the exploded guts of the star that preceded the Crab Nebula. And then famously, right in the middle, I should show you, right in the middle of the Crab Nebula, which I guess is probably somewhere right around in the middle. If you look at it in X-rays, This is an X-ray image from the Chandra X-ray Observatory. This is not a painting. I know it looks kind of artistic, but it's actually data in X-rays. In X-ray light, if gas is millions of degrees hot, it will shine in X-rays. And there's a hot region in the center. This is where the neutron star is located. It's certainly not that big and extended. This is just the area that's been, overexposed out by the brightness. And there's a disk of material that appears to be rotating around the neutron star. And there also seems to be jets, one going this way and actually another going this way. Jets of material coming off what we presume to be the magnetic poles. The neutron star is now rotating fast. It picked up a lot of angular momentum when that whole star collapsed together, and has a very strong magnetic field, and material gets jetted out along the poles. And we'll talk more about that. Okay, now that magnetic field is hugely strong. I mean, as the star collapses, not only do you spin it up to very fast speeds, neutron stars can rotate as many hundreds of times per second, but also the things are millions of degrees, very hot, rotating very fast. Sounds like a great place to generate a very strong magnetic field. Hot charged particles going around fast. And sure enough, neutron stars have the strongest magnetic fields of anything we've ever observed in space. And to sort of give you an idea of how strong the magnetic fields are, we'll compare them to things you're more familiar with, and we'll start with the unit that physicists use to quantify how strong a magnetic field is, which is the unit Gauss. One Gauss magnet is a strong magnet. If you go to a science center and there's a big strong magnet like this one, the kids are playing by putting little metal beads between and building bridges and all of that. A 1 Gauss magnet is a strong magnet. It's not something we normally come into contact with, but you might see at a science museum. The Earth's magnetic field is about half a Gauss, and that protects us from charged particles, moves them around the magnetic field and avoids the Earth. Jupiter's magnetic field is 4 Gauss, which is one of the reasons why it's so hard to maintain spacecraft close to Jupiter, because not only do you have a strong magnetic field, but Jupiter, being the huge planet it is, rotates once every 9 hours. So you've got a big magnetic field kind of swinging around really, really fast. And so when you get close to Jupiter, it's kind of like trying to work in a particle accelerator. You can see the sun's magnetic field varies depending on whether you're talking about sort of a quiet area on the sun or whether it's like a big solar flare. Solar flares happen when the magnetic field gets tightly wound, and then the particles sort of break free, and the magnetic field reattaches, and you get this burst of high energy light. That can go up to thousands of Gauss, but the normal magnetic field is about 1. MRI machine, 10,000 Gauss, right? I mean, that shows you. I mean, that changes the spin of your atoms a little bit, which is how you're able to image inside a human body. So now we go on to the neutron star stuff, and the average neutron star has about 1 billion Gauss magnetic field. We are finding some neutron stars, however, that have stupid magnetic fields. We don't really know why. Some neutron stars have stronger magnetic fields than others, but there's one we've measured that's okay. That's 1,000, 1,000,000, trillion, quadrillion, 1 quadrillion Gauss. That's amazing. That's actually as strong as a magnetic field is going to be able to get. It's not going to be able to get any stronger, because after that, it's actually going to dissipate energy by actually creating matter, making particles into existence out of just energy. That's not something that happens on Earth. So you're all familiar with Einstein's favorite: energy equals mass times the speed of light squared equals mc squared. So in a little bit of mass, like my fingernail, there's probably enough energy to blow up Milwaukee, right? Because there's a huge amount of energy in a tiny little bit of mass. And that's that's sort of that's how nuclear bombs work. You convert a tiny little bit of mass into pure energy. The energy of the magnetic field around neutron stars is so intense that it can actually take huge amounts of energy and actually start making particles. And that's the source of a lot of particles in the jets we think of neutron stars. These are actually particles that have popped into existence just because we've had the equivalent amount of energy. I mean, it's a lot of energy, right? A lot of energy in every tiny little bit of matter, but there's so much energy in the magnetic field. That's true around neutron stars. I went to a seminar, it was before the pandemic, so a couple of years ago now, and it was by the lead scientist for this mission that we'll talk about. And he said that the energy, the density of space in particles around a neutron star, like if you're right up close to a neutron star, the density of the vacuum of space is 3 times denser than pure iron. The vacuum of space. And it's because all that's there is energy. There's no gas or atoms or anything, substantive there. Just the energy of the magnetic field creates so many particles coming in out of existence, virtual particles, that it'd be 3 times the density of iron. I have no idea what it's like when the vacuum of space is 3 times the density of iron. Okay, so we mentioned that neutron stars can rotate quickly and that they have strong magnetic fields that accelerate particles in poles. And so this is how we first found neutron stars, is as neutron stars rotate, they swing these jets around the sky. And if the Earth happens to be in the way of one of these jets, then what we see is something turning on and off very quickly. So if we're up here and the jet goes, yep, there we go, yep. So I mean, as long as we can see the jet, so yep, beep, and there's another beep, where my little hand is. So we found these things in the universe that were flashing at us thousands of times a second. It's hundreds of times a second. Sorry, not thousands, but hundreds of times a second. And the name that we had for these at the time was pulsar, something that pulses in the sky. So neutron stars are, I should say, pulsars are neutron stars that we can see these beams rotating around. There are other neutron stars that we know of that are not rotating as fast. Some rotate very fast, some not so fast. And there are some neutron stars where the jets miss us, presumably. So, not all neutron stars are pulsars, but all pulsars are neutron stars. They're all just ways of observing this phenomenon. Okay, pulsars were discovered, actually, they were predicted a few decades before this, but they actually were observed first by Jocelyn Bell in 1967. Here you can see her real data using one of the radio telescopes. I should know which one, but she found something, again, turning on and off hundreds of times a second. And at first, we actually even wondered if these were artificial signals. Could they have been generated by aliens? But pretty soon people realized that they must be rotating neutron stars that were predicted. And this was a very significant result. It garnered Nobel Prizes for the people that both predicted it and observed it. That's usually how Nobel Prizes work. The people that theoretically predict something and the people that observe it share the award. In the case of Jocelyn Bell, that didn't happen. Her advisors got the Nobel Prize, and she did not. To this day, that is controversial. Jocelyn has always been very, very calm about this, because she says that, well, she was a graduate student, so maybe it was appropriate for her advisors to actually get the Nobel Prize. But I think these days we look back and think she probably got cheated out of that Nobel Prize. Now, in observing these pulses very accurately now, like observing them with atomic clocks, they're very regular, but there are things called glitches. And we can actually sort of see variations in the pulse rate of these pulsars. And they've led us to generate a lot of models as to what a neutron star might really be like. So you've got this 20-mile across super dense ball, 2 times the mass of the sun. What is that matter like? Is it a gas? Is it a fluid? Is it a solid? So these are actually diagrams of how we think neutron stars probably actually have vibrations. They almost kind of like ring like a bell. They sort of have a crust, we think, a solid crust, unbelievably dense. And that actually has vibrations that ring. And sometimes those vibrations kind of pile up on each other and may actually cause little star quakes, little bits of the crust to shift. And sometimes there'll be a neutron star where the period actually shifts permanently. It changes and then it never goes back. And that may be due to one of these sort of star quakes. And here's why neutron stars are important to you. You always need to have this slide. Okay, fun. You got stellar corpses. They're really dramatic. They rotate, they create X-rays. Why should we care? Well, these star quakes may actually affect the Earth and planets all across the galaxy. In fact, some people a little scarily think this may actually limit the lifetimes of civilizations. So these things produce stupid amounts of energy. And one that we documented was December 27th in 2004. A blast of high energy radiation hit the Earth, and it just buried the needle on a lot of our high energy satellites that were up there. And we actually were able to measure that a measurable, significant part of the atmosphere of the Earth was blown off. And it sort of strafed us. It wasn't a direct hit, but it kind of went right up the top. And some of the Earth's atmosphere just was peeled right off. And the magnetic field of the Earth was just really, got a huge amount of energy from this for a couple of days after. they trace the source of the radiation to a neutron star, one of these magnetars with a really strong magnetic field. The neutron star was 50,000 light years away. That's halfway across the Milky Way galaxy. So we think that what probably happened, just judged by kind of our computer model ideas of what these things are, is there was a little glitch, and we did record that this thing glitched. And we think that probably that super dense crust shifted by less than a centimeter, but that was the equivalent of a magnitude 23 earthquake. And the one that I like is in 200 milliseconds, more energy was released than the sun creates in 250 million years. So little smaller bursts actually occurred every 7.5 seconds as this thing orbited around. So it was like a pulsar, but a super duper pulsar. It's like, pulsar that blows your atmosphere off from 50,000 light years. So we figured we might want to know more about these things. And so here is the actual instrument that was built at Goddard Space Center. It was built right down the hall from my office. And I was always making myself, making a nuisance of myself by going in and wanting to see how it was coming along. It's about the size of a washing machine. And it was put up on a SpaceX Falcon rocket. So again, relatively inexpensive. And we smacked it on the side of the space station, mainly to get it above the atmosphere. The space station, I mean, we could have put this on a satellite, but the space station was offering, hey, if you've got a science experiment, put it on the space station. And so that's what we did. And you can see in this is actually sped up time footage of the instrument now mounted on the space station with the space station solar panels rotating in the background. There's a whole array of, they almost look like coffee cans. They're basically they're metal that sort of directs the electrons down onto the detector. Very, very hard to focus electrons reflection wise because they sort of go through things, but you can sort of direct them down onto the detector. And this does not produce images, but what it does produce is extremely accurate timing measurements down to billionths of a second as to when these X-rays arrive. And from the timing data, we can reconstruct what the surface of a neutron star is like. And here's the first reconstruction. Now, as I said, this is not an image. These things are way too small and too far away to image. But this is actually based on the timing of X-rays that came in, and that was used to produce a map. And so I'll start this little animation. The bright shapes near the bottom of the neutron star are where you would have jets coming from, jets of particles coming off. And right there, our first surprise. So we thought that neutron stars would have symmetric magnetic fields, and that the jets would go off along the poles, the north and south pole. Well, I mean, no big surprise. Something that has magnetic fields that extreme, it's not symmetric. It's a mess. There's one area that's sort of a hot spot of a dot where a jet is coming off, but then there's another area where the jet is actually sort of almost in a crescent shape. All that area is jetting material out. So first observation is like, wow, that's not the way we thought they were. And the other thing I want to call your attention to, if you look right along the edge of the neutron star in this visualization, I just want you to notice it looks a little wonky, and we're gonna come back to that. So if you look right along the edge, things are kind of distorted as they get to the edge of the neutron star, and that's going to turn out to be very important. Okay, so here's our animation of the neutron star's magnetic field. In this case, the neutron star's poles, jets are coming off the south pole region. We just picked that, completely randomly. So that's the magnetic model of what this neutron star probably looks like in terms of magnetic field. So you know at NASA that we're excited about something when we change our mission patch, and that's exactly what we did, because this is the mission patch for NICER, Sextant, NASA, Goddard, International Space Station, MIT, all of that. So in this first patch, we've got a nice neutron star with a magnetic field and 2 nice jets. We changed the mission patch to a messy magnetic field with both the jets on the bottom. So mission accomplished, we got a better mission patch out of it. Okay, now here's where I wanted to go back to that distortion. So what you're seeing when things get kind of weird along the edge of the neutron star is you're seeing the effects of gravitational lensing. Even though neutron stars are only 20 miles across, they actually bend space and time around them so much with that gravity that they actually bend things from behind so you can see behind a neutron star. So in this artist conception, you see a hot glowing neutron star, probably eclipsing, I think, maybe the plane of the Milky Way in the sky, and it's distorting because you can actually see around the neutron star. This is a way that we're going to actually use to determine the mass of these neutron stars, to figure out really how dense they are and what the interior might be like. Because the more massive something is, the more it distorts space and time. The more gravity, the more distortion. So the more massive a neutron star, the more you can see all around it. So if it's not so massive, maybe you can just see a little bit behind it. But if it's really massive, you can see more behind it. And that actually allows you to measure, from the Earth, what the mass of the neutron star is. So let's I'm going to show you a little video now. And after the video, we can come back and discuss how. So I might pause it just so you, because it's an amazing idea that you're actually using Einstein's laws to actually see behind something. And from that, we're going to be able to measure the mass.
Matter at the heart of a neutron star, the crushed remnant of a massive sun, is on the brink of becoming a black hole. For decades, scientists have wondered about the properties of that matter, the densest in the universe we can measure, and what form it takes. Now they have new insights thanks to NASA's NICER X-ray telescope on the International Space Station. A neutron star forms when a massive star's core runs out of fuel. With nothing left to fight gravity, the star collapses. Here, protons and electrons crush together to form neutrons, as well as lightweight particles called neutrinos that escape the star. The core continues to collapse until the matter at its center has twice the density of an atom's nucleus, but on a city-sized scale. When the core can't compress further, it rebounds. The expanding core crashes into the star's collapsing inner layers, creating a shockwave that rips outward through the star. The result is a powerful supernova explosion with a newborn neutron star at its center. Scientists have many questions about neutron star physics, including how squeezable is the matter in their cores? In more squeezable models, the internal pressure and density break neutrons in the center into a sea of even tinier particles, or combinations of those particles, resulting in a squishy core and a smaller star for a given mass. In some less squeezable models, the neutrons hold up against those forces, resulting in a larger star. Scientists used NICER's precise mass and size measurements of two pulsars, a kind of rapidly rotating neutron star, to narrow down how compressible these objects are. A pulsar is so dense that its strong gravity warps nearby space-time.
So just to show you, okay, so here's our eye. This little symbol means our eye is looking this way. And we're looking at a neutron star. And I mean, normally you can just see the front of something when the light that gets towards your eye is what you see. In the case of a neutron star, the light from behind the neutron star can be bent around, which means that your eye effectively sees behind it. So that's why it looks weird at the edges. You're actually seeing behind the neutron star. And so, I mean, this is the part that's amazing. And now we're going to use how massive that star is to actually see how that correlates to how big the image is on the sky.
Allowing us to see light emitted from its far side. This distortion makes it look bigger than it actually is. The more massive the pulsar, the greater the warping and the larger it appears. Scientists measure this distortion by tracking the brightness of X-ray emitting hotspots on the pulsar's surface as it spins. They can then precisely determine the pulsar's mass and radius and obtain important clues about conditions in the core. NICER used this method to analyze J0740, the heaviest known pulsar with about 2.1 times the sun's mass. Two research groups using different approaches both estimate it's about 16 miles across. NICER's measurements of J0740 and pulsar J0030 disfavor squeezable models where cores contain only quarks or other exotic matter. And J0740's size and mass together challenge less squeezable theories, where cores contain only neutrons. Physicists will have to develop new models, perhaps containing both neutrons and quarks, to explain NICER's observations. The cores of neutron stars represent matter's final, stable form, short of becoming a black hole. Scientists can't recreate those conditions in Earth laboratories. So NICER will continue to measure pulsars to probe deeper and deeper into the hearts of these mysterious objects.
So, like I said, this is just amazing. I mean, now we know that neutron stars have these, these asymmetric jets. And a lot of people ask the question, so we talked about electrons being shoved into the atoms to nuclei to become neutrons. Are there quark stars? The answer is yes. I mean, some of these there must be some other form of matter where you have quarks interacting directly with protons and neutrons, or maybe at the very core, it is some kind of quark matter, quark condensate that we've never been able to model. So, I just love the fact that we can observe with a small, inexpensive telescope, a ball that's so massive you can see on the other side of it. It's just amazing, and that's real. So I just wanted to give you a little bit of an update on Webb and talk to you a bit about one of our lesser known, cheaper missions, NICERT. I think that they're both returning incredible science. So I'll end there. And happy to take questions about anything. It doesn't have to be about this. I noticed you had the picture of the possible active volcanism on Venus. That's a big deal right now too. I mean, that's not my expertise, but I'm really thrilled about that. So I'll stop sharing my screen, and happy to take questions if you like.
All right, thanks so much, Michelle. All right, we do have a question. Applause for the. All right, we have a question from Sylvie, who's actually one of our junior members.
Sylvie.
Thank you so much. So you were discussing in your lecture how the beams coming out of pulsars, our idea of them was changed. And I was wondering if that could impact how we look at pulsar planets and how they work around their host stars.
Yeah. I mean, the pulsar planets, as you know, the first exoplanets ever detected, right, were around a pulsar. And, it does seem that these things are solid in a way, they're balls. So they do have a spin axis. And yes, it surprised us that the spin axis, with the jets were not correlated as with the poles of the spin axis. So, I mean, I think as long as the pulsar planets are not in the path of the jets, it doesn't change the model much of the pulsar planets. So I mean, I think that if one of these things is in the jet, then it's just completely irradiated. But so whether you've got pulsar planets, if the jets were symmetric, then yeah, they could be in a disk around here. If the jets are both at the South Pole, they could still be, they could still be protected. The thing that NICER has shown, which was actually something I didn't have time to include in this presentation, is that we've also seen jet regions changing their position on the surface of the neutron star. So that might not bode well. I mean, we never thought that pulsar planets were a likely place for life, because they must be some kind of remnant of the supernova explosion. But yeah, I mean, it's another thing we've talked about the TRAPPIST planets being a place that I just wish science fiction, I wouldn't have believed it. And I mean, what these pulsar planet solar systems look like must be incredible.
Thank you.
Sure.
Get the next one here.
Can we tell if any of the planets in the TRAPPIST system are tidally locked?
The assumption of the TRAPPIST system is yes, that they will be tidally locked. And one of the things that we actually use our climate supercomputer at Goddard for, I mean, the main climate models of the United States are produced at Goddard Space Flight Center. And those are things, the climate change models, the precipitation models, the drought predictions, but we actually use that Earth model for other things. And one of the things we do is we try to investigate what environments on exoplanets would be like. And one of the first things we investigated is what would an atmosphere be like on a tidally locked planet? Can you have an atmosphere? Can the atmosphere actually moderate the temperature so it's not so just hot and cold? And the answer turns out to be yes. I mean, all of these, of course, are conjectural computer models. We've not really observed, anything like that. I mean, we've made observations of tidally locked, super hot exoplanets, things that are these super hot Jupiters, and we've actually been able to clock the wind speeds on one, because this was done by the Spitzer Space Telescope some time ago. But there's a hot spot. So it's a tidally locked planet, and then sure enough, there's a hot spot facing the star, but it's actually off a little bit because there are such strong winds going around. The winds are going around at 6,000 miles an hour. that it actually carries the heat with it. And so, in this case, we've done our models on more Earth-like tidally locked planets. And it seems like you actually could get a fairly, moderate climate, even with a tidally locked planet.
I had a question about the Venus mission that was just canceled by NASA. That
They didn't cancel it. They didn't cancel it. Please, no. Oh my God, no.
seemed like it was canceled, but okay. So I was really fascinated as a chemist. I was really fascinated a few years ago when that observation was made in the UK that they thought they saw phosphine in the atmosphere of Venus. It's kind of gone back and forth. What's the current thought? Is that real? Is it not real? Is it an artifact or what?
Well, I mean, like a lot of things, and I mean, there was actually sort of a similar thing that happened to Mars. I remember when we were trying to figure out if there was methane in the atmosphere of Mars, there were some observations that said, yes, that's a very strong, that's got to be a methane detection. And then there were others where they didn't see anything. And the way it stands now with Venus and the phosphine detection. So, phosphine is a molecule, for those of you that might not be familiar, that on Earth is only created through biological processing. There's no way we know to get phosphine without life. It has to be biologically processed. And so the feature that this absorption feature in the atmosphere of Venus has been known about for decades. So the idea that something was absorbing, energy that was right around where phosphine was is something that's been known for a while. But then 2 years ago, ALMA, the Atacama Large the Atacama Large Millimeter Array, which is an incredibly powerful, accurate instrument, says that it had a good detection of phosphine. We actually also observed it using the SOFIA Airborne Observatory, Infrared Observatory. That one did not pick up phosphine. So, ALMA thinks it saw phosphine. And there are other observations that maybe think that it wasn't. So as you said, I mean, right now it's scientifically controversial. This was the Da Vinci mission and the Veritas mission are the two currently accepted missions for development for Venus. And what we're doing right now is we're trying to. I mean, another way you could get involved with science. The president's budget for science came out just a couple of weeks ago. And it did not cancel these missions, but it has them sort of postponed and included less funding than we at NASA might have liked. I mean, right now we are making our case to our funders as to why we think this is an important thing to do. In fact, I have a presentation to a congressman next Thursday where I'm getting all the latest Venus stuff up because we're going to try to make the case that this is an important mission. So the answer is, my guess is it's phosphine, seriously, because it really, the ALMA one is hard to argue with. I could be wrong, but the ALMA observation was really quite good, and you can look that up as well. The current idea is that if there is a possibility of microbial life in the atmosphere of Venus, I mean it's certainly going to be hard. Because we're thinking that round about 60 kilometers up in the atmosphere, so I mean nothing on the surface. Surface is 1,000 degrees, completely dry, but about 60 kilometers up, you do get the presence of water, but it's in these little sulfuric acid aerosol droplets. There's like little droplets of sulfuric acid. One of the problems our astrobiologists at Goddard are working on right now is, I mean, how could you actually have microbial life maybe in these very highly acidic aerosols, these little droplets of sulfuric acid? I mean, obviously a case for extremophiles. I mean, even the acid-loving microbes on Earth, this would be too much for them. But we're trying to figure out, the surface of Venus, the air pressure is like being a mile under the ocean, and so when you're 60 kilometers up, it's almost more temperate and almost kind of more fluidy, and the temperatures are much more manageable. The main problem with microbes is the water seems to be locked up in these sulfuric acid droplets. So, I mean, is there water for them to use, or is there a new kind of life that just is happy in sulfuric acid? I mean, all of those are possible. But yeah, I think it's very intriguing. And if Veritas comes to fruition, which is the mission that we're going to build at Goddard, where there's basically a sphere that we're going to drop through the atmosphere, We don't need to worry about landing gear or parachutes because it's like landing a mile under the ocean. It just kind of floats to the bottom. You know, it'll burn up quickly because nothing can survive on the surface of Venus for long. But we're hoping to actually make an in situ measurement of the phosphine. We're hoping to actually, we'll have a detector specifically tuned for that at the layers in the atmosphere where we think it might be present. And maybe there are microbes. I mean, there are microbes, as a lot of you know. There are bacteria in much of the Earth's atmosphere, even up above where commercial aircraft fly. You know, we're not even really sure of the mechanism to get them up there. It's kind of a mystery. There's lots of ideas, but you know, there's like nowhere on the Earth, you know, miles under the rock, at the bottom of the ocean, up in the atmosphere, there's microbes everywhere.
All right, thanks. I have a couple of questions from YouTube. They're actually all kind of related, so maybe I'll group them together. Susie asks, what do you think about the recent discovery of a vast number of galaxies in the early universe? And Alexander adds, what do you think all those really old galaxies, old and dense galaxies look like? And Wayne asks, do we now understand what quasars are?
Okay, so so let's sort of start at the back there. Do we now understand what quasars are? Yes, we do. And quasars are basically the very hot material circling a supermassive black hole. Black holes, of course, give off no radiation at all. They absorb everything. They have space and time itself bend back into a black hole, so there ain't nothing coming out of that. But what happens, of course, is you get this disk of hot gas attracted by the gravity of the black hole. And when you have black holes that are millions or billions of times the mass of the sun, these disks can be huge. These disks can be, you know, many light years across. The temperature is up into the millions or billions of degrees. And in some cases, and we have measurements from the Hubble Space Telescope, if you'd like to look up some of this, we have measurements of the material, the hot gas, in the very center, orbiting almost at the speed of light. So this is one of the most efficient energy sources in the universe, and they're incredibly bright. So what a quasar is if you're able to kind of see into that hot area of rotating gas around a supermassive black hole, that's where the light comes from a quasar. The other thing that you get jets of material that come away from the magnetic field of the disk. Remember, the jets coming from, they always say, oh, look at the jets coming out of the black hole. But please remember, nothing comes out of the black hole. There's a huge magnetic field created by this hot rotating disk of gas. And the magnetic poles of the disk itself pop material up into a jet. And so it's not material coming out of the black hole, but these jets can be hundreds of thousands of light years across. And they're incredible radio generators. They generate huge amounts of radio light. So whether you see lots of radio may depend on whether you're looking at the jets, whether you see a quasar, it might be actually looking into the hot material right around a black hole. If you're looking right down one of the jets, we call that a blazar, because it looks like a quasar, but it varies in brightness a lot because the jet is actually contributing brightness as well. So all of these are ways of observing these massive black holes. And like you said, I mean, the reason we see these so far away is they're so bright. You know, they're wonderfully useful because you can see them, you know, almost all the way back to the Big Bang because they're so damn bright. So the question that all of you are asking is one we're asking too. Okay, how do you get such big galaxies so soon on? And this is the first time we've ever seen something where it has the mass of the Milky Way, but it's a tiny little compact source. Are we looking at maybe just a core around a supermassive black hole? That, of course, begs the question, which has been a problem for a long time, as to how do you get such giant black holes so soon? Because right now, the only mechanism we know of to get a black hole is to have a star collapse. And, you know, and then we certainly see black holes eating each other. And you know, with gravity waves now, we observe them very routinely, black holes orbiting each other, combining to become one bigger black hole. But how do you get something that's 1 billion times the mass of the sun so soon? I mean, you've only had, you know, a couple 100 million years. And this is a problem. You know, I do not know how this happens, and nobody does. So one of the ideas is that the first generation of stars might not have even been what we get to call stars. So they call these population 3 stars. And these were stars that were made of nothing but hydrogen and helium There was the first generation. There was no other elements in the universe except hydrogen and helium. So, stars today, their atmospheres have all kinds of, pretty much the whole periodic table, a little smattering of everything in their atmospheres. And that helps the star regulate its temperature and pressure. But these first stars may have just been vast, collapsing cores of gas that maybe never even stabilized into a star. They may have just blown up right away. The universe was denser. They may have been influenced by dark matter. Seriously, dark matter has gravity. Dark matter attracts regular matter to it. So if you had collections of dark matter in the early universe, perhaps that helped these giant cores form. So maybe you started out with stars that were millions of times the mass of the sun. And they were never really a star. They never really, stabilized. They were just a huge infall of matter that then exploded, or in a supernova, or maybe just fell right into the density of a black hole. So, I mean, all of these things are possibilities. Another thing that they might take off the table, which has been out of favor for decades, is the idea of something called primordial black holes. Primordial black holes are black holes that were actually formed right after the Big Bang. As the universe expanded, some areas collapsed into these tiny little black holes, and maybe those became the seeds for these big black holes. But I mean, the fun thing is our current understanding of the early universe does not agree with our observations. And that's always job security. It's a good thing for us. So, I mean, we don't know either how we get black holes that soon. We don't know what one of these super compact galaxies would look like. They're very bright in the infrared, so they're probably giving off a lot of light. At the era they are in the universe, they may be enshrouded with dust too. The question is, because there was no dust or any other elements during that first generation of stars. It's one of the reasons they might have been just super duper huge. It'd be fun to come up with a your own artist conception of what one of these tiny super dense galaxies looks like. As we find more of them, I bet there'll be people that will start asking the question, like, if you were to make a painting of one, what would it look like? I don't know. Same thing with neutron stars. Every depiction of a neutron star, that's not what it would look like. I mean, these things are millions of degrees hot, so they're probably bright, but you're seeing behind them at the same time. And what does it mean that the density of space has 3 times that of iron around it? I mean, what does that look like? I have no idea. I would love to know.
Hi, Michelle.
Yes.
I remember learning in the 70s about neutron stars and Jocelyn Bell's discovery. Can you talk a little bit about the evolution of the theory of neutron stars before Jocelyn Bell?
Yeah, I should look up, and I did recently, because I gave a number of talks last month because it was Women's History Month. I talked a lot about Jocelyn Bell, but also all of the women at Harvard, Henrietta Leavitt and Annie Jump Cannon and Cecilia Payne. And by the way, if you don't know those names, you can invite me back for a talk about women in astronomy. But so I'm trying to remember who predicted them, and I don't remember
I think it was Zwicky, wasn't it?
Well, I know Zwicky was part of it. Yeah, you're right. So I think Zwicky was part of it. But I think that the thing that blows my mind is how recent a lot of this understanding of the nucleosynthesis, the fusion of the nuclear fusion inside supernovas really is. A lot of the understanding just goes back to seriously, like the 1930s and 40s. And I guess that's when Zwicky was working, was about then. So much less than 100 years ago, 80, 90 years ago, we really didn't understand how the sun powered itself. I mean, yes, it was thought that it was nuclear fusion, but the mechanism and then fusing different heavier elements, all of that is really fairly recent. So, yeah, I mean, I know Jocelyn Bell, I mean, the problem with detecting pulsars is that sort of time sensitivity in your measurements. I mean, nobody was looking at the sky with the expectation that a source would be turning on and off hundreds of times a second. And this is actually something that's a big deal going on right now, not just for neutron stars, but there's this whole new field opening up called time domain astrophysics. And that's that you basically set your telescopes up and keep them open for months. This is specifically popular at the South Pole during the long night in the South Pole. I have friends that go out to Antarctica on these snowcat trains. They go to the middle of nowhere and they winter over so they can look at the sky uninterrupted for months. It turns out that, things are much more variable than people were expecting. So, I mean, I think that with the advent of some of the, the big radio telescopes that came on in the 1960s, and some of the, the ability to actually see what the time variability of this stuff was, then I know Jocelyn was the first one to actually say, there it is. There's this extremely fast variation of radio signals. And the only thing that could create that would be a rotating neutron star. The fun thing about the evolution at that point is I have to reiterate that when Jocelyn first saw these things, she didn't think, oh, it's a pulsar. She had just found this unbelievably variable source in the sky. And there was a bit of excitement and concern that this was an alien beacon of some sort of, maybe a civilization had these beacons like we have GPS satellites. And the beacons allow you to navigate around the galaxy. That's what people wondered they were for a little while. And then someone said, oh, someone predicted this thing called a neutron star. And if it rotates really quickly, that's maybe what you'd see. So, it's an exciting time there for a little while where it's like, what is that? What could that possibly be? Any more detail than that, I think I'm not an expert on it exactly, but I know Jocelyn Bell, like I said, she's still around. She's gotten every other honor in the book. And we mostly think she should have gotten the Nobel Prize too.
All right, here's a softball from YouTube. Do you have any upcoming specials on PBS or any network like that?
Not that I know of. So we filmed 12 seasons of that show called How the Universe Works. And that's something, like I said, I'm not affiliated with that channel at all. They come to NASA and they film us. They interview people, and they've used me as sort of a kind of a general host to kind of set different topics up. But they don't pay us, and we're not employed by them. And I would shoot everything that they need for a season in about 2 days. So they come to either my home or my office, or occasionally they'd send me to a studio, and I would just sort of do these kind of quick introductions. And we'd shoot the whole thing in 2 days. So it's sort of strange to think that I've been on a TV show for 12 years, but I'm not actually affiliated with that business at all. Yeah, so people sometimes ask me, it's like, well, how do you get a job being a scientist on TV? It's like, well, you get a different job and you work for free. I mean, so yeah. So what happened is that there was a change in management at the Discovery Channel. I believe the Murdoch Group acquired it, and that just happened this last year. And they are rejiggering their show lineup. And unfortunately, I think what often happens is that the science is going to get largely left behind. I mean, there's a lot of shows that get more viewership. I mean, I think that How the Universe Works did pretty well for them. I think that people enjoyed the show, but to my knowledge, they're not going to make any more seasons. And, it was unfortunate. I actually was going to be part of the 60 Minutes show about Webb, but the only time they could interview me was when I was in Antarctica, and I wasn't going to cancel my Antarctic trip for an interview. So I was not on that. So I think I will time and again do some TV work, but, that's not actually my job at NASA. I'm happy to do it. We're getting ready for a number of different news campaigns we'll be doing them for Earth Day. We'll be doing them for the OSIRIS-REx that was mentioned in September 24th. The sample will come down into the Utah test range. The unfortunate thing for us, I mean, even as a communication people, is that it's being dropped into this giant big Army classified area, and so we're not going to be able to film the helicopters getting it and all of that. So. I mean, we will have people there to sort of, to say, oh yeah, we've got the sample has been acquired. They're bringing it by on a bus, but there won't be a whole lot to see for that. But then the magic starts, right? I mean, then we have hopefully acquired, fingers crossed, we've acquired a couple kilograms of, pristine samples of us as we were 4 billion years ago. Seriously, I mean, the Goddard Astrobiology Group has now identified all of the components of our DNA and RNA in meteorite samples. And, the reason we go out to get a pure sample that hasn't fallen through the atmosphere burning and then sat God knows where for God knows how long, the reason we wanted to get a pristine sample is that this is actually our biology. This is our chemistry, our prebiotic chemistry. And, this is a sample of what became you before it was you. And it's been put in deep freeze by the universe for 4 billion years. And that's just wonderful. So, we're really looking forward to getting that. That's 75% of the sample will not be opened. It will be deliberately put aside in a nitrogen environment and not opened and saved for scientists in the future. So, whatever we get back, 75% of it, the word we use is cached, like geocaching. It will be cached and put aside for when people have even better experiments and better apparatus than we do. And that's been a habit of NASA's since the beginning of samples. Just at Goddard this year, we were allowed to open one of the lunar samples. Same thing. Harrison Schmitt sealed that up on the moon 50 years ago. It was earmarked to be opened 50 years after. And so we're now experimenting with that. And there are other lunar samples that are still earmarked for the future. So, they didn't want anybody messing with it until scientists had better equipment. So we're actually saving things for our children and grandchildren in all of these very valuable sample campaigns.
Yeah, so the talk that we'll have on OSIRIS-REx will be September 22nd. So 2 days before, that'll be by John Conrad, who's one of our returning champions. And you better do those science shows, because otherwise they're going to fill up the airtime with ancient aliens. And
I know. But that's why I stopped working with the History Channel, because the History Channel had a show called The Universe, and I was one of the little hosts for that. And then right after it, I mean, literally, commercial break, and lights come up, and it was ancient aliens. And I said, these are not the same thing. I don't want somebody just casually watching to say, oh, there's NASA people talking about this. Oh, and now they're talking about UFOs. I was like, no, it's not. I don't want them cheek to jowl, because people started associating me with that. And then I was like, that's it. I mean, you're not presenting the same information. Yeah, it's a little sad, but I mean, we're making great videos. I mean, like the video I showed you today about neutron stars. We have a wonderful media group and our social media group. We've got at Goddard alone, we have like 50 young people doing social media. They are amazing. And, we've got an incredible communications group. So we're trying.
I think Lou has a question, and I have a couple from YouTube.
Okay, yeah, then I'd better head off pretty soon, but yeah, go ahead.
Michelle, actually, I got 2 questions. One that just popped up when you were talking about the human genome. You said it was a complete human genome on these meteorites that
Well, not a genome. I mean, we have not found DNA, but we have found all of the molecules that make up DNA, and not just things like amino acids. We found things called nucleobases. Nucleobases are component molecules. So it's not that we found any DNA or any genome on the meteorites, but we have found the molecules you use to make these things. And interestingly enough, on meteorites, we found more nucleobases than we use. So one possibility is that you go to Mars and maybe there's life there, but it's using different nucleobases. And so, that's something that we're prepared for now, is we have sort of a larger sample of what life might be able to make. The word for it they use at NASA is, I think it's called informational polymers. So informational polymers are, super long molecules that could do something like carry a genetic code. And so it's not that we found a genome, but we found the component chemicals that make one.
I was gonna say, because I was wondering, because my next question was gonna be, did you find any extra DNA?
Yeah. So the answer is yes, but again, not DNA, but we found similar molecules that could make a DNA-like structure, but the ones that our life does not use.
Okay, that's fascinating. So now I want to get back to your previous lecture when you were talking about coronal mass ejections. And
Yes.
you talked a little bit about here. Now, what I'm curious about, is there a predictability on the period of these things? Is it completely random? What's the worst expected damage that we can, or the minimum damage we can, encounter when one of these things happen? Will a plane fall out of the sky?
I don't know about a plane falling out of the sky. So let me back up a little bit. So as far as predictability, they are more likely every 11 years toward the solar maximum activity cycle. So the sun goes way up in activity every 11 years, then quiets down, then goes way up again. And the last couple of solar maximums we had were relatively quiet ones. This one is already turning out to be much more active, and that's not like I mean, historically there have been some really active ones. The last couple of ones have been kind of mild, and now I think we're going to get another pretty active one again. A coronal mass ejection can occur at any time, even between these 11-year maximums, but they are more likely during these 11-year times. So for the next couple of years, they are more likely than they are normally. Usually for us, this just means like great auroras and things like that. We do work with the FAA because when there's a really big, one of these big geomagnetic events, we direct pilots away from the poles where they're subject to a bit more radiation. But one of the big deals is, of course, when we have astronauts on the moon or outside the Earth's magnetic field. So that the space station is low enough, about 300 miles up, that it's largely protected by our magnetic field. So the astronauts do get a higher dose of radiation, but it's not as bad as being on the moon. One of the reasons we are hesitant to send people to the moon, and we have no idea how to keep people alive on the way to Mars. I mean, this is the problem that, a lot of the public sense, why are you guys being so slow about this? There have been several solar flares over the last couple of months that would have killed astronauts on the moon. So we need to have some way of shielding the astronauts, and we're working on that. One of the reasons we're choosing to actually be near the poles of the moon is that they may be able to shelter down in the craters and let these storms kind of go over the top. So I attended a meeting in early March where we talked about the global communication network to warn people about these storms of particles and to prepare for them. And I was left a little bit scared, to tell you the truth, that there's not as much planning in place as I would like. Even during the last solar maximum, which was in 2013, there was one big coronal mass ejection that, again, it went off kind of to the side. It didn't hit the Earth directly. And if that had gone toward us, it would have induced so much magnetic energy into the Earth's magnetic field that it would have brought down power lines. The power lines might have burned, and global grids would have gone down. And so we have a warning system with FEMA, NOAA, and NASA to coronal mass ejections are a big burst of actual hot hydrogen particles. So a solar flare is high energy light. And of course, light gets to us in 8 minutes. But one of these coronal mass ejections, this is not light, it's hot gas, hot ionized gas. And that takes a day or two. They vary in speed. And the faster these things go, the more punch they can make. And we know how fast they're going because we have satellites between us and the sun that measures this. So we'll be able to know when one of these big things is coming at us. And we'll have like a day and a half notice. And at least in the United States, we have a lot of agreements to deliberately shut down all of the electrical grids, let the storm pass, and then bring the electrical grids back up again. But the problem is, and this is what the meeting showed me, there's no global plan. Yes, we will tell China and Russia and Iran, we'll tell everyone that one of these is coming. But then what people do with that information, or whether they even have any plan to deal with that, is not something I'm very optimistic about. This is going to happen one day. Like I said, we were lucky that this really big one in early March went off on the other side of the sun, but we're going to be at a higher risk for these for the next 2 years. It is, I have no idea if I don't think it would affect anything like an airplane. I really don't, because, it's mainly just inducing a lot of electromagnetic current. So that'd be something to ask somebody else. Nobody has ever said to me that like planes would fall out of the sky, but they have said to me that our electrical grids could go down globally, and that would cause trillions of dollars of damage. Because big transponder stations and like that, they're basically built one at a time. There's no way for the globe to put in an order for 20,000 new transponder stations. So that could bring our electrical grids down and cause chaos and damage for years. And yes, that could happen.
So what would we do, protect ourselves? I mean, we run and hide in our basement? Is there some kind of shelter?
Buy a lot of toilet paper.
Yeah. So, okay, so it's worth saying, right. I mean, under the atmosphere where we are, this is not biologically dangerous. It's not going to hurt anything in terms of hurting you, causing sun. It's not like that. This is actually all electromagnetic radiation. So, I mean, it's the same thing of like, you know, it's probably not the right way to say it because light is electromagnetic radiation, but you know, it's radiation that's getting dumped into our magnetosphere, into the magnetic environment of the Earth, and that can cause electrical currents. So it's not anything that will hurt you. So it's nothing we need to worry about biologically, but we need to worry about in terms of our technology, yes. And, you know, I am concerned. I do not think that we have enough plans. I think what will probably happen is that we'll get one of these, hopefully maybe a reasonably mild one. And after that, people will start talking about it more. You know, it's, yeah, the one that happened during the last solar maximum would have been, do you guys remember that thing about 2012 and the Mayan apocalypse? So, I mean, I do communication for NASA, so I was getting all kinds of calls from people saying, you know, what's happening astronomically? Is the calendar going to align? Is the world going to end? And I'd be answering them like, would I be here at my office if I thought the world was going to end? Really? You know, when you see all the scientists like run away into the mountains and buy all the good wine, I mean, then you get worried. But you know, if we're in our office talking to you, my guess is we don't think anything bad's going to happen. And because there was nothing astronomically different in 2012, there weren't any conjunctions or anything. But I mean, we knew it was close to solar maximum. The actual solar maximum was in 2013, but if that damn thing would have hit us in 2012, and you know, everybody would have been like, "Oh, my apocalypse!" You know, I mean, I was just so glad it missed us. So, yeah, I am concerned about these things, and you know, we have, yeah.
If you hear about one of these, you know, you call us first.
No. See, I mean, like I said, we have whole plans with FEMA and with the electrical grid system in the United States and all of that. You know, there are plans here to, you know, like I said, to at least get everything shut down so that when this big pulse passes, you know, we can bring it back up again. But I mean, it kind of shocked me that there wasn't really any global plan for this. And that's, you know, I mean, we're just biding our time until one of this happens one time. Yeah.
Well, I think we've seen Don't Look Up and Idiocracy, so I think
Yeah.
your fear is probably justified.
I mean, you have to remember that the last time we actually got a direct hit by one of these. So, I mean, you do have to be like right in the line of fire. That was in 1858. Like I said, that was that Carrington event. So, you know, it's something that can happen at any time. But you know, it is statistically, you know, fairly unlikely.
Yeah, on YouTube, Roy says my dog will work just fine.
Yeah.
There's 2 questions here, hopefully quick ones. Are there any searches for phosphine on Mars? And the other is, does the AI recreation of the spinning black hole image have any real scientific value, or is it just a cool thing to do?
Okay. Let's see. I mean, the whole reason why Venus got all exciting to us is that we actually, you know, possibly detected phosphine. Certainly, we have done very, very detailed chemical analysis of the atmosphere of Mars, both in situ on the surface and from orbit, and we don't see any phosphine detection. So there are things on Mars that, and again, this is of course all published, that if we saw here on Earth would be called life detection. And I'm always a little bit, you know, reticent about this because the Curiosity rover in the last couple of months, maybe the actual experiment was last year, found layers of strata in the soil that had been actually, what's the word for it? The isotopes of carbon had been separated. That's very, very technical, but basically it's exactly what life does. Life really loves, there are 2 forms of carbon and that are fairly common, and one has an extra neutron. Both carbon atoms, one just has an extra neutron, which makes it a little bit heavier. And that means it's a little bit less chemically reactive. So life really loves the slightly lighter form of carbon. And the nature has all of this stuff all mixed together. And so we found layers in the soil where something has selected out only the light elements of carbon. In ancient times, I mean, this was probably soil that was, active, maybe a couple billion years ago. That's how we find evidence of early life on Earth. And if we had found similar strengths of this light carbon here on Earth, we would have said, that's evidence of early microbes. So we found that on Mars. And it's one of these things where, we can't say that we found evidence of life until we are 110% sure. And for this one, nobody really knows what else it could be, but is that a life detection or not? So, we don't really understand all of Mars. We don't understand the soil. I mean, in my view, the sequestration of the lighter carbon means there probably were microbes. That is by far and away the easiest, simplest way to get that. And then, so if there were microbes in the past, were there microbes now? We don't have any evidence of that now. We don't have any evidence of phosphine. We've certainly looked. And then the other one was about the AI. So one thing that we did at NASA with our supercomputer is we had, this incredibly data rich simulation of two massive black holes, supermassive black holes orbiting around each other, and all of the distortions of light and space-time that it creates. So you ask if that's, just fun or is it valuable? Well, I mean, it was amazingly hard to do. I think the person who did that simulation is Jeremy Schnittman. He's a really good friend of mine. And I think Jeremy said that on a laptop or something that would have taken like 300 years, but on the supercomputer, we got it done in about a week. It did allow simulations like that. I mean, obviously the detail of all of these distortions is not something we're going to see anytime soon. But when you think about the fact that we've got those two images of the shadows of event horizons, if you ever want to, I can do a talk on that too. The two images we have from the Event Horizon Telescope, the two dark parts of black holes you can see. Again, that one blew me away. I got goosebumps looking at that. I did not think they'd be able to see that. I was amazed. I mean, the simulations we've done have allowed us to interpret some of the brightening areas and also some of the structure in the polarization that we see. So, I mean, doing these simulations of black holes for the first time in history does have some real practical application, because although the images we're getting back from the Event Horizon Telescope are real smudgy, there is detail in them if you look carefully, and we are using the simulations to interpret that. I mean, it had never really crossed my mind before I saw those images that it doesn't matter what angle you're looking at a black hole at. That, I was like, now, how are you going to see a black hole? There's like disks of dust rotating around it. And there's all this schmutz and material around. The thing is that with the event horizon of a black hole, you can see behind it, you can see above it. The disk itself is warped, so you can see it at any angle. It never really had occurred to me that it doesn't even really matter what angle you're looking at it, because the light is all flying around in every different direction. The light itself is orbiting and curving around a black hole. Wow. So I think, in that way, it is practical. And if you ever want to see me get incredibly excited about the images look like someone put a coffee cup down, and picked it up. The smudgy ring is all you have. But when you think about what that really is, that we actually saw the event horizon, wow. I did not think we'd be able to do that. That was the kind of work my husband did, and in his honor and his memory, I love that sort of stuff. He was an interferometrist, and so I actually know how freaky those observations are. They actually may imply the existence of parallel universes. I'm not kidding. I'm a very solid scientist. If you're interested in talking and hearing about that, a couple of years ago, NPR came out to our house because I had said that the best conversations in physics I have with my husband at night in our hot tub. And so they brought a boom mic, and they put us in the hot tub, and they gave us both glasses of wine. And it's unscripted. It's just my husband and I talking about his work, which is building things like the Event Horizon Telescope. And you'll hear in his voice, because I mean, at some point I'll be saying to him, and he was British, he was really serious. And he was very, very solid, serious scientist. And at one point I'm saying to him, it's like, do you realize the implications of your work? That this means that there are multiple realities, or that, space and time don't exist the way we perceive them. He's like, oh yeah. I mean, that's Einstein. That's 100 years ago. So, the idea that our brains are not able to see the whole picture of the universe is something that is becoming more and more apparent. And why should they, right? I mean, we're little, wonderful, complex, little primates that have grown up on this planet, and we're finding that brains don't really follow along when it comes to some of these things. In order to make the measurements for the Event Horizon Telescope, we had to get the same photon, the same one, the same photon from the black hole's disk. We had to get that to arrive in 8 different locations at once and be entirely in each eight places, all of it in eight different places at the same time. And that happens when you can measure the universe to that accuracy. You find out that quantum mechanics are real if you can measure to the scale of quantum mechanics. And so we were able to use a telescope that it was effectively the size of the Earth by fooling a single particle of light into passing through telescopes in Europe, in Africa, in Asia, in Antarctica. The same photon had to be in all those places at once. And when you measure to that accuracy, you can get the light to do that.
Wow.
And it's real. It really happens.
Is Ancient Aliens anywhere near that interesting?
Oh, I know. We've got better stuff. I almost said better something else. We've got better stuff. I mean, we've got stuff that is way weirder than Ancient Aliens. I mean, if you want real, real observations, I mean, it's an image, and this image it's heartbreaking that it actually is real. That's so much better than flying saucers any day. So, yeah.
Yeah, one more.
Yeah, I better go pretty soon. Are we done?
One more question.
Okay, one more question.
Yeah, going back to the solar ejection, how safe
Yeah.
are satellites?
How safe are satellites? Varying. The GPS ones, things that are low Earth orbit are pretty good. Things that are in geosynchronous orbit, not so good. So, and I think that's GPS would be in geosynchronous farther out. So I think those would be a problem. That's how we detected some of these more recent violent events, is we had satellites that were on the other side of the solar system and they just got slammed. They just were knocked dizzy. So it would certainly be risky to the satellites that are farther away. The ones that are in low Earth orbit are better protected by the magnetic field. But for something like a Carrington event, I'm honestly not sure how that would affect a satellite that's even in low Earth orbit. So I think we probably need a heliophysicist to come that's a bit more versed in exactly what the ramifications are, because I'm sure, and we have a whole space weather action center at Goddard, and NASA headquarters has a whole space weather division, and there's some wonderful scientists there. So they would know more than I do as to what the actual technological effects would be of this.
Just ask Elon Musk.
All
Well,
right.
so the reason Elon lost those 40 satellites is we told him NASA had issued not so much of a warning, but a report that night that there was a strong geomagnetic storm, and they launched anyway, and all 40 of them fell back into the ocean. So, we saw that coming, and all we can do is advise. And good old Elon, like I said, I was really kind of amused about him talking about NPR being state-sponsored or government-sponsored media, because people forget that Elon Musk is a government contractor. We pay for those rockets. He wouldn't make his payroll without NASA buying the Falcon rockets. And, he's got the contract to do the moon lander. We can't land on the moon until he delivers the moon lander. He has the contract to build it. So, he is a taxpayer funded entity. And, I am always, we buy his products because they're good. People say, are you in competition with Elon Musk? No. The Falcon rockets are great. We're hoping for more Falcon Heavies. We're hoping for moon landers. It's a good company, and we hope that they build the stuff. But you've been paying for it, and the reason he's super rich is government contracts. Him calling NPR state sponsored is.
Do we have a Twitter page, or do we have one anymore?
Even NASA's been arguing. Well, not arguing, just discussing. What do you do? What do you do when Twitter's now kind of gone crazy? So, Yeah. Anyway, listen, I will head off, but it was nice to talk to all of you.
Let's thank Michelle for a great talk.
Bye.
Take care.
Thank you. Bye.
Wow, that was great. Thank you, Jeremy, for arranging that. It's just super. But now the moment you've all been waiting for, we're going to draw some numbers. Ken, would you like to take it from here?
Hey,
Is it
actually,
too
let
late
Janet draw the numbers, so I.
Is it too late to buy one? Is it too late to buy one?
We have a lot of anxious people here.
Okay, sorry, anxious people. Okay, we'll have Janet, the president, draw the first one.
378075.
It's not my ticket because I bought one over here.
Oh, we have dinner.
Good, good.
Whatever you get first, whatever's here.
First choice. This man told me he never won anything in his life. Okay, yeah, we'll do the next one. Okay, the next winner is 378